Hi, I'm Marcelo Mendoza and I will present time series classification for rumor detection. This work is jointly authored with Fernanda Weiss and Evangelos Milos. Social network and rumors are very important topics for research because many of the information that is spread in social networks is unverified as a start of the spread of the information. For instance, in this example, we can observe that a user is posting about an information about fake protests in Austin, Texas. But many people at the start of the rumor spread is asking for concrete evidence. But other people has the tendency to believe in this information and then they repost this information. After a while, Donald Trump propagates this information, commenting this information, and then many people access to this original information, because if very visible people propagate some information, this information reach more users in the entire network. The point here is that this information was false, but this information reached many people in the network. What is a rumor? A rumor is a story which may not be true. Why rumors are so important? Because we are living in a post-truth era where facts doesn't matter. What is really important is the impact of a given information, independently of the level of veracity that this information has. Why is this so important? Because this information is spread very fast in social networks, and people adopt an emotional attitude in front of this information. That is the goal of the people that is spreading false information in social network. The final objective is to polarize users. We work in this study with 4 levels of rumors, of different types of rumors. True rumors, that are rumors that are confirmed, non-rumors, that is a story related to confirmed facts, false rumor, that are rumors that was denied with evidence, and unverified, that is a rumor that at the end of a timeline has not been confirmed. So we have these 4 types of rumors. Social networks and rumors spread through propagation trees, where the root of the tree is the original post and many people can aggregate more information or can comment or deny this original information. All this process takes time, so the characterization of the whole process through time is an essential element for the analysis of rumor spread. We observed this 10 years ago, showing that the messages of the first persons that posted after the earthquake, the Chilean earthquake in 2010, were very important for the rest of the people in the network, creating cascade of information that were commenting on this original post hours later of the earthquake. Why is this so important for rumor detection? Because these propagation patterns show some differences in terms of veracities. We can observe that non-rumors and rumors has different patterns of propagation. We observed this 10 years ago also, showing that people tend to deny and question false rumors because a type of common sense in users tend to be or to indicate to this person that this information is unbelievable. So people naturally question or deny. But other people can affirm false rumor. Almost the 45% of the people tend to believe in false rumors, propagating them. So our technical approach is based on dynamic time warping, matching in time series, to measure the distances between these time series, looking for the best alignment between these time series. And the distance, the basis distance for dynamic time warping, is the Euclidean distance. Why we use this? Because we group up time series to identify time series prototypes using dynamic barycenter averaging. And the distance between this to compute this prototype is based on dynamic time warping. Prototypes will be very important in this study to create a time series classification method. Why time series and rumors, or which type of patterns can be observed in time series and rumors? We can observe that true rumors tend to concentrate more activity during the first hours of the spread, but false rumors do not. They has the activity distributed along the timeline. Non-rumors has more peaks of energy, of activity during the spread of the rumor. And unverified rumors are at some extent similar to non-rumors, and then they will be very difficult to separate by the time series classifier. Why we need another study in fake news detection? Because many studies in rumor detection based in machine learning has many limitations. Overfitting, language dependence, poor transferability, time obsolescence, etc. All these limitations related to the data used to train the model or to the model itself. So the goal of our study is to test the utility of time series in this problem, trying to show if they are helpful to for the detection of rumors. Our approach is time series classification, so it's technically very hard because we have many alternative or different preprocessing steps for time series classification. So we have to choose between a specific technique for time series augmentation, scaling, piecewise approximation, and finally training, testing, splitting to identify the the data used to train and to validate the classifier. So the time series used in this study has a temporal basis that defines the points observed in a time series. We used 7 indicators to create a multivariate time series for each rumor, considering the number of posts, retweets, replies, total number of tweets, number of distinct users who posted messages, the number of followers, and the number of followees of users who posted messages in each interval. And we studied many options to train a time series classifier. These are all the options studied by us, but the key building blocks are the ones shown here. So we have a block for inception time that we will use as a pre-processing block to train a fully convolutional neural network, that will be used to encode the time series and then to train a classifier. Our proposal is based on clustering because we use clustering to identify time series prototypes. So in a first step, we use time series k-means to group similar time series, and then these prototypes are fed into a second clustering algorithm based on hypergraph clustering, where hyperedges connect nodes if they belong to the same prototype or if they belong to the same class. So this hypergraph clustering look for the class alignment. So the key idea is to align the prototypes with the classes of the problem. And the output of this clustering algorithm will provide prototypes alignment with the classes of the problem. At the outcome of the last layer of our approach, we use pairwise training dataset to train a Siamese neural network, showing to the network time series are different prototypes, asking to the network to distinguish between these pairs if they belong to the same class or if they belong to different classes. To achieve this purpose, we use the contrastive loss function that is based on distances between pairs, and that will reward pairs that belong to the same class and will penalize pairs of time series that belong to different classes. In our experiments, we work with two datasets, and in a first stage, we analyzed the different configurations for time series classification, and these yellow lines show the best configuration for each of the three models evaluated in our study. For the Siamese network, we found that the best configuration was based on min-max scaling and piecewise aggregation. And for the fully convolutional neural network, we used the min-max scaling also and the time series augmentation data strategy. And for the fully convolutional neural network, combined with the inception time block, the min-max scaling and the time series augmentation strategy was also the best configuration. Then we will use this configuration to evaluate in both datasets the performance with other methods of the state of the art. But before the validation, we evaluate also the impact of each time series in time series classification, dropping out this time series and computing the performance. This evaluation allows us to identify that two time series were neutral in terms of impact. These time series are the number of posts and the number of retweets. Maybe because this time series correlates with the other time series of the representation. So we remove this, and finally we work with 5 time series for the purposes of the validation process. And the results are shown in table 4 and 5. We show the results in Twitter 15 for time series classifiers, basic classifiers, for classifiers based on text, and for classifiers based on text and graph. And we can observe here that the best method of its class in time series classifier is the method proposed by us. But when we aggregate another information sources, the performance improves. So by including more data into the model, we can observe an improvement in the model performance. And this observation is also valid for Twitter 16. Finally, we evaluate the models in a time-sensitive scenario using a timeout. So acquiring the data during the first 3 hours, 6 hours, 12 hours, or 24 hours. And we observe in this evaluation in terms of F1 score that the performance of the models based on text and based on graph is heavily based on the complete data. And when we acquire the data only during the first hours of the propagation rumor spread, this performance decreases significantly. On the other hand, we can observe that the fully convolutional neural network for time series and the Siamese neural network for time series outperforms the state-of-the-art in an early detection scenario. This observation is also valid for Twitter 16. So, the main finding of this study is the time series utility, very helpful for time-sensitive detection in rumors. So the conclusion of this study is that we have introduced the first time series classification-based models for rumor detection, and our results show that these models are competitive in early detection scenarios, and that our experiments show the state-of-the-art rumor detection, CSI, has a strong dependence on the availability of complete information, limiting its usefulness in time-sensitive scenarios. The main finding and the highlight of this presentation is that time-based features are helpful for time-sensitive classification. Thanks.